So yeah, it's an honor to be able to speak at this meeting in memory of my memory of Eric. I'll say a few words about Eric first. I was just thinking that okay, there are two countries in which I've lived. There are the Netherlands and Germany. But apart from these two countries, I think the country in which I've spent most time is actually Sweden. And I think that has a lot to do with Eric. So in a way, Eric has been with me for my entire sort of scientific life. So basically the first papers that I read sort of seriously when I was a master's student for my master's thesis were the papers by Eric and my supervisor, Ike Moerdijk, who concerned categories with W types and models of constructive set theory. And they were also the basis for my master's thesis and also for my PhD thesis. Also, when I actually became a PhD student, the first foreign visit I made was actually to Sweden, to Uppsala, to the other author of these papers. So that was Eric. And I remember that very well. He took me to some restaurants, kind of fancy for my standards, I mean, he was just a very, very, very kind host. And I've been in Sweden many more times. I've been in Uppsala, I've been in Stockholm, and I always enjoy talking to him. Always very much appreciated his input on all the things that I'm working on. And even to this very day, I noticed that if I'm working on something, then often when I do some literature research, I mean, his papers appear. So he's always there in the background of many of the things that I've done, including the things on non-standard arithmetic, sheaf models for constructive logic, many things. Of course, he has also been kind of very instrumental in sort of the development of homotopy type theory. I think the first workshop on homotopy type theory was organized in Uppsala by Eric and Richard Gardner, I think, at that point. So basically, he has been there all the time, and that's why it is such a shock still to know that he's not there anymore, and he's not able to comment on the work that I'm doing today, and actually that I'm going to talk about today. So I think I would have very much appreciated his feedback. So in fact, it is more like on the constructive intersection of logic and topology, which was, I think, also where Eric very much was at home. So it is what I'm going to talk about is work in progress, I should say. Still things to be done. I'm also not entirely certain whether in every respect I've got all the details quite right yet, but so that's also why actually I'm kind of interested in receiving input, no longer from Eric, but from you. So it very much connects to his interest: sheaf toposes, categorical logic, constructive topology, and even in a way setoids. I should also say that this is joint work with a master's student who recently graduated at the University of Amsterdam, Daniel Figueroa. And I think he's still interested in doing a PhD and is still looking for a job. So maybe keep that in mind. Okay. So what I wanted to talk about is, in a way, I'm acting like an arrogant category theorist. So what I mean by that is there is an interesting area of mathematics out there. It's called continuous model theory. And I try to understand what they're doing. And one thing I'm sort of convinced of is that the concepts of categorical logic that I know and love and have been developed in the categorical tradition are the right concepts to understand what they're doing. They're not phrasing it in these terms, but yeah, so basically what I'm trying is some sort of categorical understanding of the sort of the practice of the area in continuous model theory. And maybe I should say right away, it's a kind of fuzzy model theory in which the truth values are not just 0 and 1, but can be an arbitrary element in the unit interval. It has applications in analysis. It's in a way kind of old. It has at least been 50 years old. Yeah, I think so, more than 50 years old. So it is an established part of model theory, maybe not the most prominent one, but there's definitely a tradition. And I should also say that that we're not the first ones to actually try to understand what happens in this area in categorical terms. So I mentioned 2 preprints on this slide. Both of them are still preprints as far as I know. They have not been published. And I think, yeah, so there's an important paper by Bill Lovier. Should I keep an eye on the chat? Can the chair maybe keep an eye on the chat? So there's an important paper in the background, which is Bill Lovier's paper on the connection between matrix spaces and enriched categories and some sort of generalized logic. If you would ask me to sort of explain what the difference is between our approach and their approach, I would say that we are the more arrogant in the sense that we are sort of take for granted that the concepts that we know from categorical logic are the right concepts. They start modifying some of the basic concepts of categorical logic more so that it fits with what happens in continuous model theory. We are more sort of trying to squeeze continuous model theory into the standard categorical logic framework. Okay. The way we do this is by using the language of hyperdoctrines. Yeah, so I think hyperdoctrines are indeed, I think, a standard concept in categorical logic. So what we're looking at is pseudo functors from some category with finite limits into the category of preorders and monotone maps. The way to think about this is that the objects in the category C are like types or sorts. So we assume that the sorts are close to the products. The functions in the category C are like function symbols, if you want. And so if you have such a sort X and you apply P to X, you get a certain preorder, and that's like the preorder of predicates where they're sort of ordered by yeah, some sort of implication. So that's the basic setup, going back to Lovier. So we will distinguish between different levels of doctrines. So the ones that will, basically all the doctrines, hyperdoctrines in this talk are coherent hyperdoctrines. That basically means there are models, there are going to be models of coherent logic. So coherent logic is basically logic, basically the logic of and or and exists, and maybe let's throw in equality as well. So basically a coherent formula is one which involves these connectives, and the ones that we can interpret in coherent hyperdoctrines. Basically, in coherent hyperdoctrines, we can interpret implications between such coherent formulas. So there are 2 things which are missing to just get full first order logic. That's the universal quantifier, and that's the implication. So there is this, if we add both of them, then we get like a first order hyperdoctrine. And And there is an intermediate level, which doesn't really have a standard name. I think for the purposes of this talk, I've called it universally coherent hyperdoctrines. So that just has a universal universal quantifier, but not necessarily an implication. Implication, I mean implication in the constructive sense, like a heighting implication. So yeah, so all these connectors are interpreted in the usual way as in categorical logic, as either certain adjoints or as certain meets and joins in these between these preorders. Okay. What I will be so what I will also be looking at is functors, like morphisms between these hyperdoctrines. So by a morphism between these hyperdoctrines, I will mean something like a functor between the underlying categories, so it maps sorts to sorts, functions to functions, and then it should also mention map predicates to predicates. That is what is done by this, let me see, by this natural transformation eta over here. And then we expect it to preserve all the structures. So that's what the definition basically says. Let's say if it's between coherent hyperdoctrines, it would preserve something like meets and joins and existential quantifiers. And an important class of morphisms of hyperdoctrines is one, I don't think it has a standard name, but I'll call them embeddings. That's where the underlying functor is full and faithful. And we have this also like full and faithfulness between the predicates. So in that case, I will think of the hyperdoctrine Q as some sort of conservative extension of the hyperdoctrine P. It basically, the world from P basically embeds like fully and faithfully inside the world of Q. So Q has maybe more sorts, more types, more function symbols and more relations, but what it said about the old relations is exactly what P said about these things. So it's like a conservative extension. So these are the notions from categorical logic that we will mostly be talking about. And it's basically that we want to sort of squeeze continuous model theory into these terms, whether they want it or not. Okay, good. So a hyperdoctrine for continuous logic, that's what we're after. Yes, I mentioned earlier, so the continuous model theory is a subject with a branch of model theory with applications and analysis. It goes back to a monograph by Cheng and Kiesler from 1966. I think my impression is, I mean, I haven't done a detailed research, sort of investigation of the literature, but that there are different approaches, and that what we'll mostly be basing our work on is like more a modern treatment, as you can find it, for example, in this paper called Model Theory for Matrix Structures by these 4 model theorists. So the idea is, as I said, it's kind of like a fuzzy logic. So the truth formulas are interpreted as, so the truth values can be anything inside the unit interval. What is a bit odd at first is that they consider 0 to be true and 1 to be false. They have good reasons for doing this, which I'll explain. But it's a bit hard to get used to at first. The way we interpret the sorts are, okay, these can be, I mean, if you pick up a book, you will see different things. You will say maybe matrix spaces, maybe pseudo matrix spaces, maybe complete matrix spaces, maybe with some diameter, and so on and so forth. Just to fix something, I will fix it to be complete matrix spaces with diameter 1. Which, and with diameter 1 means that the distance between 2 points is always at most 1. So function symbols are interpreted as uniformly continuous functions. So if you for example, if you look in this text, like Model Theory for Matrix Structures, you will be struck by how often they mention the word uniform continuity. That really seems to be sort of the that's for them the important class of functions that they want to consider. And indeed, function symbols are interpreted as uniformly continuous functions. And then relation symbols are, sort of like take values inside the unit interval. And the way they interpret inequality is as the distance relation. So x is equal to y is interpreted as the distance between x and y, which is some value between 0 and 1. And now you can understand why 0 is true, because if the distance between 2 points is 0, that actually means that the 2 points are equal. So that's the reason for sort of reversing the standard convention. So I think a good way of thinking about these truth values is like distance from the truth. Like, and so if you have zero distance from the truth, then you're true. If you have maximal distance from the truth, then you're false. Okay. Oh yeah, so maybe I should say first something also about the connectives. So in a way, there are no surprises here, I think, for like conjunction and disjunction. So in conjunction is the maximum and disjunction is the minimum. Okay, the surprise is that it's this way around, but that's because 0 is true and 1 is false. And also the existential quantifier is the infimum and universal quantifier is the supreme. That makes sense, at least their convention. And there is actually, if you open the text and open these books, you will also see that they say, yeah, actually, for our purposes, we can treat any uniformly continuous operation, which from the unit interval to the power n to the unit interval as a logical connective. So what our analysis is going to be is actually going to be hard to reconcile with this idea. So I'll say more about this later. I mean, some of the other approaches, like the papers on the preprints I mentioned earlier, really do take this very seriously. But here is where there is some tension between our reconstruction and what actually happens in continuous model theory. So, I mean, initially you might think, okay, now this is a hyperduction for continuous model theory or continuous logic. It's very easy. We know what the sorts, the function symbols, and the predicates are. So the hyperdoctrine that we have to consider is, okay, so the sorts, so like if you say, right, C mat 1 for the category of complete matrix spaces of diameter at most 1 and uniformly continuous functions between them, that's going to be the underlying category. It has products, obviously. And then the hyperdoctrine should send such a matrix space X to the set of uniformly continuous functions from X to the unit interval. And the action is given by the factoriality. It comes from precomposition. Okay, so that's obvious. That's sort of immediately given. But the question is how, but there's one ingredient missing because we have to order these predicates. And actually, if you open these texts, I think it is very hard to sort of get an idea of what the order of these things should be. I mean, the text, the continuous model theory literature doesn't really give you a good answer, I think, to that question. And that's basically where the problem starts. I mean, there is an obvious thing you can try, and that is basically, okay, that's sort of by pointwise, just order them pointwise, or maybe reverse pointwise. But that doesn't seem to be quite right. And it's, yeah. So the question is, well, how to respond to this. There's actually an interesting quote in this respect from in the paper, Model Theory for Matrix Structures that I mentioned earlier. And yeah, maybe I should just read it. So one of the subtleties of continuous first-order logic is that it is essentially a positive logic. So they mean that it has no implication or negation. In particular, there's no direct way to express an implication between conditions. This is inconvenient in applications since many natural mathematical properties are stated using implications. However, when working in a saturated model or in all models of the theory, this obstacle can be clarified and often overcome in a natural way, which we explain here. Okay, and then there is this proposition that they formulate. So this is, I think, at least in the text that I know, I mean, the closest they get to sort of formulating an implication. And actually, it's a bit ambiguous because I think I would make a distinction between something like a consequence, like phi following from phi, like a consequence relation, and having an implication, which is like an internalized version of this consequence relation. And I don't think the text, I mean, the text is a bit ambiguous. I mean, they seem to talk about this, but they mean this, I think. And then they write, yeah, so then I'm sort of mostly intrigued by this. That doesn't work. So I'm mostly intrigued by this second condition that they have over here, which basically says, I mean, so I think the idea is here that psi will follow from phi if it's sort of so if for every epsilon bigger than 0, there exists a delta bigger than 0, such that sort of uniformly, if phi is below delta, then psi is below epsilon. And that's it. Okay, so that's a condition we can, I mean, that is something I can take over. So, I mean, if we just very naively just copy this, then we actually do get a way in which we can order, I mean, general predicates like this. And that's as follows. I mean, we just say that it's a kind of uniform continuity condition, which makes sense because they all seem to be obsessed with uniform continuity. So that, if you want to get your psi below epsilon, then there exists a delta such that as long as phi is below delta, then your psi will be below epsilon, sort of uniformly in all x. And then indeed, you get a uniformly coherent hyperdoctrine, so an hyperdoctrine with these connectives. They have their expected interpretations as max, min, infinite sup. But we have a consequence relation, but we still do not really have an implication, at least not a heighting implication. So you can prove that it's not the first order hyperdoctrine. Okay, but I mean, this is the closest. I mean, using the language of hyperdoctrines, I think is the closest we get to sort of making sense of their basic definitions. So the goal we set ourselves, Daniel and I, is to find an embedding of this particular hyperdoctrine, the coherent hyperdoctrine we call CMT here, into the subobject hyperdoctrine of a topos. So we want to find a topos E, and we want to sort of regard this. I mean, usually in topos theory, predicates are interpreted as subobjects, so we want to also be able to see the predicates in continuous model theory as subobjects in a topos, and we want this to be an embedding. So the word embedding is kind of important here. So we want to, so this world has to be some sort of conservative extension of the world CMT. So, and one thing I think this might be interesting also, I mean, so for the continuous model theorists is that they have this problem of implication. And of course, the topos has an implication. So maybe we can help them with finding their implication. Okay, so how do we do this? So in a way, we do this in two steps. First, we try to embed this hyperdoctrine CMT into the subobject hyperdoctrine of a pre-topos. Okay, and then we will move towards the topos, which actually after, once we've mapped it to that of a pre-topos is not so difficult anymore. So first, this is the first step, mapping to a pre-topos. So how do we do this? So the first step is to define a kind of simpler version of this hyperdoctrine CMT, where we just basically, in a way, we throw away all the sort of metric stuff. So we have this hyperdoctrine U on, you can see my mouse, right? Yeah. So we have this hyperdoctrine U on the category of sets. We map a set X to the collection of functions from X to unit interval, just all functions. And we pre-order it in this particular way, so we can get phi as close to 0 as we want if phi is at least sufficiently close to 0. I mean, that's the intuition, and in fact, this condition is classically equivalent, and not constructively, equivalent to saying that whenever phi converges to 0, psi converges to 0 as well. So actually, I think this is kind of nice because this is kind of intuitive. So it basically says that 0 is true, right? So psi follows from phi means whenever phi converges to the truth, psi does as well. I think this in a way is an interesting notion of consequence relation, I think, just per se, to think about. So that is this, so we can organize it in this hyperdoctrine, and again, this is a universally coherent hyperdoctrine with min, max, and supernins, but it's not first order. It does not have a Heiting implication. So we have a counterexample of a surgeon implication which does not exist. Okay. So yeah, okay, yeah. So what can we do with this hyperdoctrine U? Well, actually, there's a general construction that we can do on any coherent hyperdoctrine, or let's say even regular hyperdoctrine. But okay, let's say we have a coherent hyperdoctrine, and now we can take like a setoid-like construction. So what we do is we take objects to be pairs XR, where X is some object in the category C, and this R is an element of the hyperdoctrine. So it's like a binary predicate on R in the sense of the hyperdoctrine, and it has to be an equivalence relation in the sense of the doctrine. And then we can, so the notion of morphisms is that of sort of functional relations. So if we have two such animals, equivalence relations, then functional relation is a relation on X times Y, which is sort of compatible with R and S. It is functional, and it is single valued in the sense of S. And then you identify two such if they're sort of extensionally the same. So I think this is just a well-known construction in the language, in the world of hyperdoctrines, very similar to setoids. So, so we can perform this construction on this hyperdoctrine U that I started with, like the uniform, yeah. And the funny thing is, the category of this category CMAT1 embeds into this category ERU. So the thing is that, so if you give me a metric space with diameter 1, then this D is just going to be a function from X times X to unit interval. And if you think, okay, so but wait a sec, what are the objects here? Well, it's a set X together with a relation, binary relation on X in the sense of U, which is also a function from X times X to unit interval. Okay, So this relation has to be reflexive in the sense of the hyperdoctrine, which actually translates to the fact that the distance between x and x has to be 0. And its relation has to be symmetric in the sense of the hyperdoctrine, which basically is true because the distance relation is symmetric. And then you have to check, for example, that it is transitive, and that relates to become something like, so if you want to get a distance between x and y, x and z below epsilon, then you should find a delta such that the maximum of the distance between x and y and z is below some delta. And if you choose your delta, it becomes like analysis. Yeah? So I mean, you choose your delta to be half epsilon, and you use the triangle inequality, and you're done. So yeah, so this transitivity is because of the triangle inequality. And so actually this is very reminiscent to what happens in Lovier's paper on rich categories and metric spaces. So yeah, if you have a uniform, I mean, but there's extensor functions as well. So if you have a uniformly continuous function between two metric spaces, then you can turn it into a predicate. 0, 1 valued predicate on x times y is just fxy is the distance between f of x and y. And the really cool thing is that this functor is full and faithful. So it basically means that every functional relation comes from a unique uniformly continuous functions between these complete metric spaces. We actually conjecture, and that's what we're working on right now, is that actually this is an equivalence of categories, which is really fun, if it is true. So we also expect this functor, I would suspect this functor to be essentially surjective. So, and the proof that we have in mind how this should work is that we start with such an object as R in ERU, and we want to sort of find a complete metric space, which is sort of isomorphic to it in the sense of ERU. So what we do is, every object in ERU can be turned into what is called a uniform space. Then this can be approximated by a pseudo-metric space. Then that can be turned into a metric space, and that can then be turned into a complete metric space. So I think it's kind of easy to see that every such thing becomes a uniform space. Then we have to turn it, then that the pseudo-metric space can be turned into a metric space, and then a complete metric space. Yeah, that's something we've done. The crucial step is that we have to turn every uniform space into a pseudo-metric space. And actually, it's interesting because I think Ishihara is going to talk about precisely this construction, I think tomorrow morning. And is also something which appears in Eric's paper, at least a constructive version of it. So there again, we can, there's a connection here. So this is would be kind of a logical reconstruction of the category of complete metric spaces and uniformly continuous maps.
Benno, sorry to interrupt. I've lost sight of what U was. Can you remind us what U was?
Oh, U is this hyperdoctrine.
Okay. Right. So X isn't a metric space.
No, X is just a set. So yeah, it's a hyperdoctrine on the category set. Sets and functions. Predicates are just arbitrary functions to the unit interval. But the crucial thing is this particular way in which we order the predicates, which is sort of inspired by uniform continuity.
Yep.
Yeah.
Okay. Yeah. Thanks.
Sure. Yeah. Okay. So this is but this is not our pre-topos. We wanted to turn it into a pre-topos. And the way we do this is actually by just not looking into equivalence relations, but of what are called the partial equivalence relations. So if we have a coherent hyperdoctrine, we can also take the kind of partial equivalence relations on that hyperdoctrine. So so now your pairs XR, where X is a set and R is a symmetric and transitive relation. So we drop reflexivity. Then we look at functional relations between them. Yeah, so there's some tweaks here, but again, I think this is a standard construction. Also, it's basically the tripos to topos construction. Yeah, so but it works for coherent hyperdoctrines as well. Then you would get a coherent category. But in our case, when we do this on the hyperdoctrine U, we actually get a pre-topos. So it's a coherent category, but actually a bit more. It also has some degree of universal quantification, namely for the reflexive objects, if you want. And indeed, there is an embedding of coherent hyperdoctrines from CMT to this category U of partial equivalence relations on U and the subobjects of that. So we have an embedding of hyperdoctrines from CMT to the subobject hyperdoctrines on this category of partial equivalence relations. So that's the first step. But the second step is then to move this, to turn this pre-topos into a topos. And in fact, that's kind of a standard thing. So there's this result which says that if you can take a small coherent category, then you can take the coherent topology on this category. Then you turn it into a Grothendieck topology, site. And then you have the Uneda embedding of this original category in the category of sheaves on that. And that's going to be a coherent embedding, and it will actually preserve any universal quantifiers which exist in C. Something which was also exploited in Eric's paper on constructive sheaf semantics. So that we can just take off the shelf. So there is no real creativity needed here. Right? So what we can then do is, okay, so I mean, if we just take the definition quite literally of pair, this category pair of U is going to be large, but at least, okay, let's assume that we have some universe and all the sets. And we only sort of use sets from that universe in the construction of this hyperdoctrine. And in that case, this is going to be a small category. And then we can just apply this theorem. So we take this category of partial equivalence relations, we take the coherent topology on it, and then we take sheaves. And that gives us actually, yeah, so if we do that, we get this sheaf topos, and we claim that actually there's going to be an embedding of universally coherent hyperdoctrines from this CMT into this sheaf topos together with its subobjects. So that was the goal, and that's the way we achieve it. Also note that basically by doing this, we basically have constructed a sheaf topos in which this category of complete metric spaces and uniformly continuous maps embeds fully and faithfully. So it sits inside there in a fully faithful way. All right, so those are the results. And there's still a lot of questions, things to think about. So maybe the first question is, yeah, so is this useful for the purposes of continuous model theory? In particular, of course, I think this topos has an implication something they seem to lack, and they, according to this quote, is useful in application. So that is something that could potentially be exploited. I mean, I must confess that I don't know too much about the applications of continuous model theory, so I can't really say how plausible it is that that's going to work. Also, I think, of course, the topos is a model of higher order logic, so it's not just first order logic. So it has, of course, toposes have extremely rich structure. That is something that could potentially be exploited. An interesting question, I think, also is, I mean, in some way, you could say that we have built a topos of sheaves on a category of topological spaces in continuous maps, which is a kind of, yeah, I mean, we're not the first to do such a thing. So, I mean, these are things are used, for example, to model continuity principles. So the question, for example, could be, do any continuity principles hold in this topos? Is that useful? For instance, we have an embedding of the complete, so we have the embedding of the category of complete matrix spaces inside the sheaf topos. So we get a version of the unit interval just from this embedding, of course, but then we also have in the sheaf topos, there is also going to be a unit interval because it's a sheaf topos and these unit intervals exist. I mean, maybe you can different constructions using daisy kings or Cauchy wheels or what have you. So is there any relation between these two objects? I think is another sort of very natural question. I have no idea. Of course, there's still this conjecture about ERU that we are working on. I'm optimistic, but yeah, we'll see. And then Daniel, in his master thesis, actually has some negative results as well. So I mentioned that in continuous model theory, people want to regard every uniformly continuous operation from the unit interval to the power n to the unit interval as a kind of logical connective. And that is something that simply is not true in our setting. I don't know. I mean, maybe we only have to look at certain kinds of sub-objects, but then we have thought about this and maybe, but we don't know of a good sort of condition that would sort of make this, maybe this only works for certain kind of predicates, but we don't know how to formulate that in categorical terms. We also don't know how important this is. Whether this is just something they think they can do or whether this is also, for example, an important for application. I have no idea. Another thing which I think is very natural is just to look at variation. So, in particular, on this hyperdoctrine U. So this is, in particular, to try to define different consequences, like order the predicates in different ways. So now we've done this in a kind of uniform continuity way. But there is also a Lipschitz way, for instance. Okay, so this is the Lipschitz condition. I'm pretty certain that also gives you universally coherent hyperdoctrine. So again, you could maybe, and what happens, for example, if you take the equivalence relations, category of equivalence relations on this, how is that related to the category of complete matrix spaces and Lipschitz continuous maps? I don't know, it probably embeds, but is it again an equivalence? I don't know. And then, of course, there's this thing that maybe you wanted to do all along the way, and then that might actually be connected to complete ultra matrix spaces and non-increasing maps. Maybe. I don't know. So there, I think these two things are kind of obvious variations. Maybe there are more that we haven't thought of yet. But I think definitely here there is quite a lot of space for further exploration. So that's that's where I wanted to end. I thank you for your attention, and I also want to thank Eric again for all the help and support that he has given me.
Let us thank Benno. Let us silent applause. Thank you. That was interesting. There are some questions. In particular, I think Torsten had some questions. You want to post them?
Yes. So grateful. Some questions actually got answered already on the chat. That was very useful.
Okay.
Thank you. Maybe I've got some more answers. But my last question maybe is, can you give a more explicit description of the sub-object classifier in this topos? Is there an easy way to understand it? I mean,
yeah, we haven't actually thought too much about that. Okay, so the closed sieves on.
Sure. Yeah.
Okay, I have no idea.
Okay. Maybe I can ask you a question you can answer. Sorry. Okay. Or maybe also not. Because there are some people who in computer science who study something called fuzzy logic, which I think is maybe related to what you're doing, like astrology is related to astronomy. But maybe you can give a more positive comment on this.
This has been recorded, right? No.
Oh, my boss! Oh no! I'm stuck.
No, I don't know. Delete. Yeah, no. Yeah, so I also don't really know. I mean, yes, I think my impression is also that the literature on fuzzy logic is rather uneven in terms of quality. And yeah, so we really started from continuous model theory. That felt very solid, like very solid work. But it's true, I think. I'm a bit unsure what the precise aims of the fuzzy logic people are, but maybe it has some relevance for.
They're a bit fuzzy, I think.
I think they're also a bit fuzzy about what they want to do with it. Yeah, yeah, that's also my impression. Yeah, yeah.
Then there's a comment from Fosco in chat. Do you want to say it out loud, or?
Yeah, this is just a random thought. I cannot claim I have a very precise way of helping for the conjecture, but I was struck by. Can you please go back to slide 19? It was when you defined the functor f in the conjecture.
Yes.
Exactly. I think you can regard the action of f as the way it is defined. It seemingly associates to a metric space, to a uniformly continuous function, sort of a representable profunctor if you look at x and y as enriched categories in the sense of Lovier. And if there is a bicategory where ER of U embeds, then F is an equivalence just because of the way it is defined. Because the action of an equipment, of a pro-arrow equipment for CMET1 would be exactly acting as F, capital F is defined.
Ah, okay.
So essentially your conjecture is this capital F captures the essential image of a pro-arrow equipment.
Okay.
And, this is probably not helpful. It's just a way to raising the conjecture, but
okay.
CMET1 is a 2 category, and probably
sure.
the R of U as suitable representable profunctors enriched over 0, 1 or 0 infinity, depending on your.
Okay.
In this case, 0, 1. And if this is possible, then F, capital F, turns out to be just the usual construction that builds a Praro equipment out of a 2 category, because CMAT1 is just, well, almost categories enriched over 0, 1.
Yes. Yeah, I think I sort of understand where you want to take this, and we'd have to think more about this. Yeah.
It's probably just it might be a dead end, but the way in which Aleph is defined is exactly reminding of that kind of representable construction.
Okay. So, yeah. Okay. So I'll look into it. Yeah. Thanks.
May I ask a question?
Hello, Thomas.
Okay. Now, I would like to know which kind of formal system for the logic the continuous model theory guys suggest. Maybe none, but I mean, in ordinary model theory, you're doing Gödel's completeness theorem. So do they have a suggested axiomatization for the logic, or don't they?
No, they don't.
I see.
No, they're model theorists. They don't need that. They don't need proof calculation.
I see.
I mean, yeah.
I see.
Yeah.
Good.
Yeah, no. I mean,
that's bad, I'd say, but yeah.
Maybe they're just not a model theorist. I mean, one thing which is interesting, I think, is that. So how was it? I mean, there is a certain axiom. I mean, if you're working in classical matter theory, there's a certain axiom which holds in these hyperdruck twins, which is not true, which is not a tautology. I mean, it's not intuitionistically valid, and that's this constant domains axiom, which sort of says that, what is it? Or distributes over the universal quantifier, something like that. That seems to hold. Anyway, I mean, that's if you want to form it, I mean, that actually means that if you want to axiomatize it, that would have to be one of the axioms, I think.
So there's a couple of raised hands. Steve Vickers.
Yeah, 2 slides before the end, you mentioned the idea of arbitrary uniformly continuous maps as connectives, and you said that was incompatible with consequence.
Yes.
So is that just a matter of monotonicity, or is there more to it than that?
I think the explanation, I mean, yeah, so I think there's just a very, I mean, yeah, so Daniel has a technical proposition in his thesis, but the way I would sort of understand it is that in a way, our implication, yeah, I mean, there's a certain tension between this idea and the idea that somehow, basically, our notion of consequence only, in a way, looks at the behavior around 0. And in a sense, which, I mean, if you're far away from 0, whether you're on half or 3/4 or 1 is in a way completely irrelevant. So
does that lost then? Have you gone beyond the for all epsilon there exists delta definition? Because that was everywhere, wasn't it? Not just around 0.
No. But an end is no. Yeah. So these x's here are just an elements of some set in general. So what I mean is that if I would just redefine these functions phi and psi would turn it into something completely different outside a neighborhood of 0, basically. I mean, nothing changes. Yeah, from what I remember, that is I think that is difficult to reconcile. I mean, for instance, they claim that the function which sends x to 1 minus x is a perfectly fine connective, and there's even some tendency to see that as a form of negation. But that I think is one example of a connective which doesn't really make sense in our world.
Right.
Because I think, yeah, so the point is that this function behaves different on 1.5. And from our purposes, 1.5 are just far away from 0 and should be treated the same way. But if you then plug in 1 in this, you get 0, which is a significant thing. And if you plug in a half, you get a half again, which in a way still is like far away from 0.
Yeah.
So that's the tension, I think.
Yeah. So I mean, what it made me think was if you change the topology on 0, 1, if you use the Coase-Scott topology, so you're dealing with the upper reals, then all your continuous maps are forced to be monotone, and you're going to get a different theory. So you don't have arbitrary soups anymore. You've still got arbitrary ints. So your logic is weaker. And in fact, it's beginning to look like geometric logic, which would still be relevant to the topos. So I was wondering what happens if you change the topology there.
I haven't thought about that at all.
And we do know the theory of metric spaces still works well. And even quasi-metric spaces works well with the upper Scott topology, the upper reals.
Okay, yeah. Okay, something to think about. Yeah, thanks for the suggestion. I have no idea what would happen.
I had another question. Just the slide before last, you mentioned ultrametric spaces, and I wondered why what you've written suggested ultrametric spaces.
Oh, I can explain that. No, I mean, if this has to do with transitivity. So if in this particular, if in this hyperdoctrine, I want to write down transitivity, what it will relate to is something like the maximum of the distance between x and y and z is an upper bound for the distance between x and z.
Right.
So
so that's looking like the ultrametric inequality.
Indeed, that's the point. So transitivity and so transitivity becomes so that's why I write ultrametric here in connection with this hyperdoctrine.
All right, we're getting to the end of the time slot.
Okay.
So I see there are more raised hands. Maybe you can ask Benno offline. Let's thank Benno again.